Well, now we will start with the module modeling and go to the next complication to be incorporated in the modeling of the modules. We have finished the simplified case number 1. Now we will go to case number 2. In case number 2, we are basically talking about permeate flux. In the earlier case, we considered permeate flux was constant. Now we are talking about permeate flux is proportional to transmembrane pressure drop. Pressure drop and completely retentive membrane. That means Cp is equal to 0, and permeate flux is proportional to transmembrane pressure drop means J is equal to Lp del P. That means we are neglecting the osmotic pressure compared to the feed pressure. That means negligible. Negligible osmotic pressure. So, again we will start with the spiral wound module or plate and frame. That means we are talking about flow through rectangular channel. Now, the geometry remains the same. It is basically two channels, and it will be this, let us say H, that is the middle of the channel, this Q in, the material going into the system, Q out, the flow rate, the material that is going out of the system, and you will be having presence of membrane. And this case, in fact, this is not constant. This Jw is not constant, it will be a function of x simply because the delta p is a function of x in this case as well. But this is still not a realistic case because we are neglecting the osmotic pressure effects. Okay. So, in the next case, case number 3, we will be dealing with that. Okay. But before that, let us solve this case because we can have an analytical solution in this case and see how it works out for this case. Okay. So, J becomes Lp del P, and if you look into the expression of the transmembrane pressure drop governing equation, the governing equation becomes d square delta p divided by dx square is equal to 3 mu h cube times j. Okay. So, we have already derived that. I am just taking up the expression. So, now we are putting j is equal to Lp del P. So, this becomes d square delta p dx square is equal to 3 mu by h cube Lp delta p. Lp is nothing but the membrane permeability. So, so the difference is that this time the right hand side is not constant. Okay. So, the earlier case it was this, since J was itself was taken as constant, but this time it will not be constant. And let us look into the boundary conditions. At x is equal to 0, you had delta p is equal to delta p in. At x is equal to 0, you have d delta p dx will be nothing but 3 mu divided by 2 h cube w q in. Okay. So, let us see how this can be tackled. we consider, let us say lambda is equal to root over 3 mu LP over h cube. So, in that case this equation can be written down as d square delta p dx square is nothing but minus lambda square delta p will be equal to 0. Now, this is a second order ordinary differential equation with the characteristic with the solution in the form of e to the power mx, and you will be getting a characteristic equation in terms of m square minus lambda square, right. So, the solution will be in the form of e to the power mx e to the power lambda x, right. The characteristic equation that will be getting, it will be in the form of e to the power mx only. So, you will be getting m square minus lambda square will be equal to 0, m will be plus minus lambda, right. So, you will be getting a solution delta p as a function of x as some constant multiplied by e to the power lambda x plus some constant c 2 e to the power minus lambda x. Okay. Now, this constant c 1 and c 2 can be evaluated from the boundary conditions that we have already specified, that is the first one is at x is equal to 0, you will be having delta p is equal to delta p in. Okay. So, you will be getting c 1 plus c 2 will be nothing but delta p in. Okay. And the second boundary condition, in order to get the second boundary condition, you have to take the derivative of this expression and evaluate it at x is equal to 0 and see what you get. Delta p x is equal to c 1 e to the power lambda x plus c 2 e to the power minus lambda x. So, derivative of that will give you d delta p dx is equal to c 1 lambda e to the power lambda x minus c 2 lambda e to the power minus lambda x. Evaluate this at x is equal to 0. So, you will be getting c 1 minus c 2 times lambda. Okay. And the second, if you remember, the second boundary condition becomes x is equal to 0, d delta p dx is equal to minus 3 mu divided by 2 h cube w q in, and you will be getting consequently c 2 minus c 1 times lambda. This minus will be taken care of, 3 mu divided by 2 h cube w q in. Okay. So, you can take lambda to the denominator. So, this becomes divided by lambda. Okay. And you had already c 1 c 2 plus c 1 is equal to delta p in. Okay. Now, you can have you can evaluate this, you can just add them up, can get the expression of c 1, can get the expression of c 2. Please do that, I am not doing it, and you please fill up the couple of steps. And if you rearrange the solution will become will be constituted with the cos h hyperbolic sine and hyperbolic cos functions. Okay. So, I am just going to write down the final expression. So, you can really fill these gaps up, and the expression that you will be getting is that delta p x divided by delta p I is nothing but cos h lambda x minus 3 by 2 mu q I divided by 2 h cube divided by h cube w lambda, w is the width, divided by delta p I, delta p I means at the inlet, sin h lambda x. Okay. This is the so this becomes right. This is the pressure profile, transmembrane pressure profile. Transmembrane pressure profile as a function of x. Okay, as a function of axial distance. Now, this can be translated into the axial pressure drop. Okay. So, the profile of axial pressure drop becomes delta pi minus delta px. This becomes delta pi 1 minus cos h lambda x plus 3 by 2 mu qy divided by h cube w lambda sin h lambda x, where the parameter lambda is given by under root 3 mu Lp divided by h cube. Okay. So, this expression gives the profiles of axial pressure drop. In fact, if you remember, if you have already done the other courses that I am talking about, the chemical engineering courses, in all the chemical engineering equipment, whenever you are talking about the flow through a tube or for a any column design, let us say packed bed or say fluidized bed or anything, this pressure drop calculation becomes very important. Okay, everywhere you are doing the pressure drop calculation. The idea is one has to calculate the pressure, because in a flowing system pressure has to decrease, okay, because of the friction and other fittings and other losses. So, you have to design a pump accordingly, so that you can overcome that much of pressure drop and can deliver at a particular flow rate, at a desired flow rate. Okay. So, all these calculations are basically aimed to design a particular equipment. What is that equipment? The equipment is either a pump in case of flow of the liquids, or a compressor in case of flow of a gas. Okay. That is why pressure drop calculation becomes very important in all the chemical engineering equipments. Okay. So, this gives the profile of axial pressure drop, and one can get the total pressure drop across the length of the module. So, this becomes delta pi minus delta pl is equal to delta pi 1 minus cos h lambda l plus 3 mu qi divided by 2 h cube w lambda sin h lambda l. Okay. Now, we can define the fractional recovery of the feed. Okay. Of the complete module, this is defined as Qp divided by Q in. That means flow rate you are getting out of the permeate, total flow rate in permeate divided by flow rate in. That means material going out of in the permeate divided material going into the system per unit time. Okay. So, this becomes 2 W L P. In this case, since here delta P is a function of x, and you will be having 0 to L delta P x dx divided by Qi. Now, you have the expression of delta P as a function of x, just going to substitute there, and one can get this expression of fractional recovery of feed over the complete module. Okay. Again, I am just putting the, I am giving you the final expression. What you have to just simply do, we have already derived the expression of delta Px, substitute there, carry out this integration and get the value of fractional recovery, expression of fractional recovery. If you do that, what you will be getting is F is equal to 2W Lp delta Pi divided by lambda times Qi bracket sin hyperbolic lambda L minus 3 mu Qi divided by 2 h cube W lambda delta Pi cos h lambda L minus 1. It becomes a complicated expression. So, one can put the various values of width of the channel, permeability of the membrane, the delta P transmembrane pressure drop at the inlet, that is known to you because you have a pressure gauge there. Qi is the flow rate, that is also known to you because you have the rotometer there. Length is known, all the other parameters are known. Lambda is basically a parameter, it is a combined parameter of viscosity, permeability, channel geometry, that is H, so that will be known. So one can estimate the total recovery of the feed in the permeate, and the profile of permeate flux one can obtain because profile of permeate flux is very simple to obtain in this case. The permeate flux profile becomes, because you have J as a function of LP times delta P, where delta P is a function of x, you can get a profile of permeate flux LP delta P I cos h lambda x minus 3 mu q I divided by 2 h cube w lambda L lambda delta P I times sin h lambda x. Okay, right. So one can get the expression of how the permeate flux varies as a function of x in this case, and one can integrate it out over the full length of the module and can get the how much is the length average permeate flux you are going to get. Now using one can get the expression of how velocity, the cross flow velocity is varying as a function of x. If you look into the governing equation of Q, you just get the governing equation of Q, that is the flow rate, and substitute Q is equal to two x h u, right, 2 w, okay, w becomes x over that differential element, right, and this will be the area times so this is the cross sectional area, right. It should be w times h, width times height, not x. That becomes the cross sectional area of the flow multiplied by the u, that will be q, right. So if you substitute in the governing equation of q, if you remember we had a governing equation of q, dq dx is equal to minus 2 w j, something like that. Okay, we had substitute in that expression and see what you get. If you really do that, you will be getting du dx is equal to minus j over h. Okay, so this is the governing equation how u is varying as a function of x, how the velocity, the axial velocity is varying as a function of x. In fact, it is decreasing because you are taking some material out of it. Okay, and you know the expression of j as a function of x, we just derived it and substitute it there and integrate over the x and can get the value of u at any x location or at the end of the channel if you want. So if you really carry out this integration, this becomes du, and this will be from inlet ui to any location u, LP delta Pi divided by h, okay, 0 to x, okay, velocity is u at any location x, 3 mu qi divided by 2 h cube w lambda delta Pi sin h lambda x minus cos h lambda x dx. If you carry out this integration and rearrange, you will be getting the profile of cross flow velocity. U as ux divided by u in is nothing but 1 minus LP delta Pi divided by h lambda ui sin h lambda x minus 3 mu qi divided by 2h cube w lambda delta pi cos h lambda x minus 1. And if you replace x by L, then you will be getting the velocity at the end of the module and how it varies. So, this expression gives how u varies as a function of x, and if you put x is equal to L, that will give you the velocity at the end of the channel. Okay. Now, next you can do the what we have done till now. We have used the Navier-Stokes equation to get the governing equation of delta p. What we did a overall material balance over a differential element, you got the governing equation of q or u. Now, if you do a species balance equation or a solute balance equation over the differential element, you will be getting an expression of concentration. Okay. Let us do that. Concentration or solute balance equation, solute balance over a differential element. Okay. This is located at x, this is located at x plus delta x. So, this thickness is basically nothing but delta x, and C in and Q in, or let us say U in, is the velocity at the inlet, C in is the concentration at the inlet, C out and U out are basically the concentration of the solute and the velocity that is going out of the system, and you are going to get the permeate. But remember, if since we are talking about a completely retentive membrane, the Cp will be equal to 0 on both sides. You are going to basically recover pure water out of this. So, if you really do a material balance or solute balance, what you are going to get is that you are going to get ddx of u times C times 2 times W times H becomes equal to 0, because nothing is from the permeate side, nothing is going out, because no concentration of the solute, that is no solute is going out. So, therefore, u times 2WH, 2W is the surface area. Okay, that so u times 2WH is basically the cross sectional area. Okay, why it is 2? Because H is the half height. So, that is the total height multiplied by the W, that gives the cross sectional area, multiplied by U, that will be the total flow rate multiplied by the concentration, that will be giving you the kg per meter square second. Okay. So, that will be equal to 0, and what you are going to get is that U at x, C at x must be equal to U at I and C at I. Okay. That means U times C is constant, ddx of U C equal to 0 means U times C is constant. That means at any location U times C is nothing but the product at the inlet. Now, we know the variation or the expression of U at x and divided by U y. So, from this you can get what is the profile of concentration as a function of x. So, C at x divided by C in is nothing but U I divided by U of x. That simply means you have already obtained the expression of U x there, just substitute it there. So, okay. So, you will be getting okay, I think this itself, I think we have derived U by U y. So, it will be inverse of that. So, it becomes 1 by 1 minus L p delta p in divided by H lambda U in sin H lambda x minus 3 mu q y divided by 2 H cube W lambda delta p in cos H lambda x minus 1. this simply means that since u is varying as a function of x and it is a decreasing function of x, as you go down the channel or the module, the velocity will be decreasing because you are extracting the material out of it. Okay, as the velocity decreases, this numerator, the whole Cx by Ci will be increasing, right. So basically in the downstream, of the module, concentration is increasing. That means the solution becomes more concentrated. Why it will become more concentrated? Because you are not, it is a totally retentive membrane and you are extracting the water out of it, so it becomes more concentrated. Concentration increases. So if you now plot a profile, your pressure drop will increase as you go down, your flux will decrease something like this, your velocity will be decreased, it will be decreasing. Okay, this will be u, the cross flow velocity, your concentration will be increasing. Okay, this is the profile of concentration. So you can get various profiles of all the parameters: velocity, concentration, permeate flux, as well as the transmembrane pressure drop. Okay, and one can do the appropriate selection of the pump accordingly. Okay. Now let us, so this gives a more realistic system when your delta P transmembrane pressure drop or operating pressure drop becomes very high compared to the osmotic pressure drop. Now let us look into the tubular module, because we should, as we have discussed the modules earlier, there are two coordinate systems that we can think of among all the modules, either tubular, radial polar coordinate, or in the rectangular coordinate. So we have done the rectangular polar coordinate. Let us look into the tubular coordinate or the radial coordinate useful for the tubular modules, and how the expression changes and how they look like. Equation of motion or Navier-Stokes equation will give you the expression of q or u. What is that? The u becomes r square by 8 mu divided by minus dp dx, and we have already seen dp dx is nothing but d delta p dx, okay, the transmembrane pressure drop. So we write it safely as r square divided by 8 mu minus d delta p dx. Okay, so you can get an expression of d delta p dx as minus 8 mu over r square times u. Now again you can write down a material balance over a differential element. As we have done earlier, you will be going to get, and assuming that density of the feed is equal to density of the permeate, you are going to get du dx is equal to minus 2j over r. Okay, and since the osmotic pressure is negligible, j is nothing but Lp times delta p. So this will be nothing but minus 2 Lp delta p over r, and just substitute. So that means you differentiate this expression with respect to x once more. So differentiate with respect to x. So what you get is d square delta p by dx square is nothing but minus 8 mu over r square du dx, and substitute du dx here. So you are going to get the governing equation of transmembrane pressure drop. Okay, so if you really do that, I am not going, just put it there, you will be getting 16 mu Lp by r cube into delta p. Okay, so we are going to write down the expression of transmembrane pressure drop In case of the tubular module, d square delta p dx square becomes 16 mu Lp over r cube times delta p. Okay. So, and we require two boundary conditions for delta p, and we have already seen how they will be set. At x is equal to 0, both the boundary conditions have to be specified. Delta p is equal to delta p in, and at x equal to 0, you have d delta p dx is nothing but 8 minus 8 mu over r square times u velocity in, okay, u times in. Now, using these two boundary conditions, now when both the boundaries are specified, when both the boundary conditions are specified at the same boundary, there is a specific name to this system. Do you know that? This is known as the Cauchy boundary condition. Cauchy boundary conditions are basically both boundaries are specified at the same location. The same location. Now, if you really solve this set of equation with this boundary condition, I am just going to write down the final expression. This becomes, solution becomes delta p as a function of x is nothing but delta p I. Again, it will form by the cos h hyperbolic cos and sine functions, cos h mx minus beta times sin h mx, where m is equal to under root 16 mu Lp divided by r cube and beta equal to 8 mu u inlet divided by m r square. Okay. And the axial pressure drop profile can be obtained profile along the module becomes delta p I minus delta p x is equal to delta p I 1 minus cos h m x plus beta sin h m x, and the total axial pressure drop along the module across the module when we replace x by L. Okay. So, since you know the pressure drop profile, one can go to the expression of permeate flux, that is J is equal to L p delta p. Since we know the delta p as a function of x, one can get the permeate flux as a function of x. Okay. So, if you really do that, just substituting the delta p profile into the expression of J x, one can get the profile of the permeate flux. Permeate flux profile becomes J times x is Lp times delta p I cos h mx minus beta sin h mx, and one can go to the integration or length averaging over the full length and can get the value of the length averaged permeate flux. Okay. So, length averaged permeate flux over the length becomes nothing but 1 over L 0 to L dx. Just put the expression and integrate it out, you will be getting it. Similarly, when you are talking about we can get the as we have discussed earlier, one can get the expression of profile of cross flow velocity. We can do the same thing. I am just writing the final expression. U divided by U at inlet is nothing but 1 minus 2 LP divided by MR times delta PI sin h mx plus beta 1 minus cos h mx bracket n, and one can get the concentration at any location, that is U at any location x, and one can get the concentration profile at any location of x. This is the inverse of Ui divided U in divided by U at x, and this is 1 over this whole expression 1 minus 2 LP over MR in the bracket. Okay. So, as velocity decreases, the concentration increases because you are extracting the material out of it. Now, in that so that goes the derivation for the case where your permeate flux is proportional to delta P with the negligible osmotic pressure. In the final more realistic case, we will be doing the when osmotic pressure is not really negligible and it will be some substantial value and of significance. So, case number 3 is basically partially retentive membrane. That means Cp is not equal to 0. That is a very realistic case, right? Some amount of solute will be retained by the membrane, some amount is not. Partially retentive membrane, and the osmotic pressure is not negligible. Okay. Fine. So, we do the again we do the similar type of calculations. We start with the Navier-Stokes equation and hook it up with the velocity, and you will be getting the governing equation with respect to governing equation of transmembrane pressure drop with respect to x. Then you do the overall material balance, that will give you the governing equation of the velocity, cross flow velocity. You do an overall you do a solute balance equation within the differential element, that will give you the profile of the concentration, solute concentration. So, we go step by step. So, Navier-Stokes equation, and that will give the equation of motion. Let us do in a spiral wound module. Okay. The first thing we are going to do for the spiral wound module, rectangular coordinate. That means rectangular coordinate. Okay. d delta P dx, this becomes minus 3 mu q divided by 2 h cube by w. Okay. That you get from the equation of motion, and substitute in the flow rate, q is equal to 2 w h times u in the above equation, because this is the cross sectional area and this is the velocity. 2 comes because 2 times the h is the half height, 2h is the full height. Okay. So, this becomes d delta P dx becomes minus 3 mu u divided by h square. Okay. So, J becomes now in this case, since the osmotic pressure is not negligible, we can use the Darcy's law as J is equal to LP delta P minus delta pi, and J becomes LP delta P minus B1 CM RR. I think we already derived it number of times. B2 CM square 1 minus RR square minus B3 CM cube 1 minus RR whole cube. Okay. So, we already know the governing equation of delta P, and here we will be getting the okay. So, this becomes J becomes a function of membrane surface concentration, and solute balance over the differential element gives you d u c dx is equal to minus j c p divided by h. Okay. You can really derive this thing. I am not doing it. Okay. So, if you want, you can do on a differential element. Okay. Let's say these at x plus delta x, u at location x. Okay. C at location x, and this is u and c at x plus delta x. Okay. So, and what is going out is nothing but J, and Cp is the permeate concentration. So, total solute coming into the system is u times cross sectional area, right, multiplied by C, that is the total solute going into the system. So, if you do that, what is the cross sectional area? W times 2H, okay, that is the cross sectional area. So, U C to WH, that is at x, in is equal to out, and what is out? U to UC WH at x plus delta x plus the material that is going out with the permeate. Okay. J times meter cube per meter square second. What is the surface area? Surface area is nothing but W times delta x, that is the surface area. So, meter cube per meter square second multiplied by meter square. So, and then multiplied by Cp. This becomes the solvent multiplied by the concentration. So, meter cube, so it becomes kg per second, right. So, what you get is that 2 WH common, C at x plus delta x minus C at x is equal to minus J times Cp W times delta x, right. There are two surfaces, so there will be a 2 here, W times delta x multiplied by 2. So, there will be 2 here. So, your 2 W will be cancelling. So, this becomes C at x plus delta x minus C at x divided by delta x is equal to minus J C P divided by H. Right, U C, right here, no, instead of W it will be U. Right, U C at x plus delta x. Okay, this one, no, it's okay. Right, correct. U C at x plus delta x minus U C. So, it will be a differentiation of d dx of U C. That is correct, because U is also function of x. So, it is d dx of U C is minus J C P divided by H, and we have already derived the expression of du dc du dx earlier, and so you just open it up, that means u dc dx plus c du dx, and substitute du dx from the earlier expression, and finally you will be getting u dc dx is equal to j times h c minus Cp. Okay. So, expression of dc dx will be nothing but j divided by u times h c minus Cp. Now, Cp is the permeate concentration. Now, you got an ordinary differential equation of delta P, you got an ordinary differential equation of delta of U, you got an ordinary differential. So, from the Navier-Stokes equation and combination of the overall material balance, you got the ODE or the governing equation of delta P. From the overall material balance over the differential element, you will be getting the governing equation of U, and from solute balance equation over the differential element, we will be getting the, and combining with the expression of U, you will be getting the governing equation of C. Now, what is now left is how J is related to Cm and how Cm is related to Cp, that interface. Okay. So, that will be taking recourse to the definition of mass transfer coefficient, and we will calculate that k times Cm minus C is nothing but d del C del y at y is equal to 0. If you remember that the value of C that we are putting here, that is nothing but the cross sectional average bulk concentration, right. It is basically, it is nothing but the cross sectional average concentration. Okay. So, this is basically the bulk concentration we are talking about earlier. Okay. So, therefore, if you remember the definition of mass transfer coefficient, we had k times concentration at the wall minus concentration at the bulk. So, here in this case it is not C naught, it is basically C that is appearing in the governing equation. So, my bulk conditions are now a function of x as far as the module is concerned. Initially, previously we had they are treated as constant. Now, they will be function of x. There is the only difference. Now, let us see. And at the steady state, the boundary condition on the membrane surface becomes J times, if you remember, Cm minus Cp is equal to minus d del C del y at y is equal to 0, right. So, that we have already used so many times. Now, I will equate these two equations because the right hand sides are both same. So, you will be getting k times Cm minus C is nothing but J times Cm times real retention RR. I eliminate Cm, I eliminate Cp in favor of Cm multiplied with the real retention RR, which is constant. Now, we have already got an expression of J, probably J is equal to Lp into delta P minus delta pi, and we have expressed how delta pi can be expressed in terms of Cm and real retention, etc. So, just insert there here, insert that equation here. So, you will be getting k times Cm minus C divided by Cm RR Lp is equal to delta P minus A1 Cm plus A2 Cm square plus A3 Cm cube, where A1 is nothing but B1 RR, A2 is nothing but B2 1 minus RR square, and A3 is nothing but B3 1 minus RR whole cube. Okay. This expression gives you an algebraic relationship between the bulk concentration and membrane surface concentration. So, when I am writing J is equal to Lp into delta pi, and delta pi is a function of Cm, now I should have a relation between the membrane surface concentration Cm and the bulk concentration C, because all my governing equations are now in C. So, this is the algebraic relation that gives you an interface or the relationship between the surface concentration on membrane and the bulk concentration C. Now, what is the expression of mass transfer coefficient you can take? Now, we can insert the generalized mass transfer coefficient that we have derived for the porous conduit. So, this model, the third case, deals with all the complexities involved in this system. Okay. So, the k, if you remembered, the value, the expression of mass transfer coefficient was 1 over I u d square by h x raised to the power 1 upon 3 from the similarity solution, and I can be expressed, the definite integral can be calculated from 0 to infinity exponential minus eta cube by 3 minus 0.42 lambda eta times d eta, where the suction parameter lambda is nothing but j bar, that is the length average permeate flux, divided by d times L multiplied by u d square raised to the power 1 upon 3, where j bar is nothing but 1 over L 0 to L jx dx. Okay. So the what is the algorithm? The algorithm goes something like this. You guess a value of j bar. Okay, guess a value of j bar, and once you guess a value of j bar, the length average permeate flux, you will be getting the expression of lambda. You will be in a position to evaluate the expression of I, the integration definite integral I. Once you will be able to integrate I, you will be able to calculate k, mass transfer coefficient, as a function of x. Now in this expression, what is this value of u? U is basically the bulk velocity we are talking about. This was replaced by u naught earlier. This bulk velocity is now a function of x, and we have a governing equation of x of u as du dx is equal to something. Okay. So once you can calculate the value of x, then you can calculate the value of so k as a function of x will be known. So this gives you Cm as the relationship between Cm and C. Now all the three governing equations, if you remember, all the three ODEs, ODE number 1 will be the governing equation of delta p. You had d square delta p dx square is equal to something, or d delta p dx is equal to as a function of u. Okay. So you have the ODE number 2, that gives you the overall material balance, that gives you du dx is equal to some function from f1. ODE 3, that gives you solute valence equation over the differential element, that gives you dc dx is equal to some functional form f2. Now these three ODEs, and they are basically initial value problem. You know the initial condition for all of them. So these three ODEs has to be solved by using RK4 method, and every step of RK4 you have to solve this algebraic equation. You have to solve this algebraic equation to update the value of Cm or C. Okay. That way you will be generating after integration. So basically it is a system of DAE, differential algebraic equation. You have three differential equation, one algebraic equation coupled. Okay. You have to solve this system of DAE IVP problems, their initial value problem, and you will be generating the profile of delta p as a function of x, u as a function of x, c as a function of x, Cm as a function of x, and j as a function of x. So what is the output? Output will be delta p as a function of x, u as a function of x, c as a function of x, Cm as a function of x, because c and Cm are related by the algebraic equation, mass transfer coefficient as a function of x, Cp as a function of x, because Cp is nothing but Cm into 1 minus real tension, and of course j as a function of x. After doing this RK4, you calculate, you do a length averaging, you use a Simpson's rule or a trapezoidal rule. I think Simpson is better in this case, 3/4 or 3/8 Simpson. So 1 over 0 to L jx dx. Calculate the value of length averaged permeate flux and check whether this calculated length averaged permeate flux is matching with the guess value of the length averaged permeate flux or not. Okay. That way one can generate the full profile of all the dependent variable and can get the value of transmodule pressure drop as well as the concentration of the permeate at the outlet of the module. So you have to guess a value of length average permeate flux, redo these calculations, and once getting the profile, you have to do a Simpson's averaging over the length and calculate the length average permeate flux and check whether they are equal or not. If not, you have to iterate once again. Okay. So that is how we have to do a actual model, module calculations or module modeling. Okay. So, in the next class, so I will stop here. In the next class, what we will do, we will extend this method for the tubular module and for the turbulent flow regime. Okay. Thank you.